All right. All right. So I've started the recording. And hi, Lakshmikant. Good morning. And so Srinivas's question is: we do not have an option of updating a record or to update the records. Okay, because it is stored in HDFS. But HBase also storing data in HDFS. How is it possible? Okay, so it's about the functionality they are providing. So it is not a problem. So question is that Hive also stores in HDFS and HBase also stores in HDFS. How come Hive does not have an option to update or insert the records and HBase does not have? Okay. So all right. So the way it works, see, if you can edit files in HDFS, it's not that you cannot change the files in HDFS. Meaning, if you change it, it will basically mean that you are basically writing further. All right. Now, the way editing happens in HDFS is by mentioning one more version, right? Okay, okay. So the all right. So first, let's discuss things one by one. So Hive does not provide editing. That's a conscious choice Hive has taken. Hive was supposed to be like Pig, only a tool that converts SQL into MapReduce. Okay, so Hive was supposed to be a tool that's only role is to convert MapReduce into MapReduce. Sorry, I'm so sorry. All right. Okay. So the job of Hive was to convert SQL into MapReduce, and that is why Hive does not provide update in the records. Though if you see the newer versions of Hive which they are working on, they call it Stinger.next. Hive also provides the insert and update of the records. Alright? So in the similar manner, HBase provides you writing ahead. Okay, so it's a choice. It's not a limitation by HDFS, due to which Hive does not provide the writing or inserting the record. It is a choice which Hive made. All right. In case of H, and the impression that HDFS gives you that you cannot alter the file, and that is in some way correct. So, because HDFS, the way it has been designed is HDFS is write ahead kind of a file, for write ahead kind of file system, meaning append only file system. You can append to an existing file, but if you want to edit it, you will have to delete the old one and then create a new one or some version of that one. Delete a block, add a block. All right. So that is something HDFS does. All right. Any questions at this point? All right. Okay, so I think I'm able to answer Srinivas, so I'll move ahead. Okay, great. Now, so till yesterday we were talking about a new tool called Spark, or a new framework called Spark, where you can create brilliant queries which can immediately return result. And how does it work? All right. So the core concept behind Spark is something called resilient distributed dataset. Just like we have an HDFS, Spark creates one more layer of the data, which is called resilience distributed dataset. So whatever file we want to operate upon. So if you guys remember when we talked about pig, what we were doing, first step is to load the data. Then all the operations are on the data, saying filter this and iterate over this. So all of the functions were on the top of data. In the similar behavior, Spark has come up with this construct of operating upon the data. And first step in Spark also is to load the data. And load data means creating the resilience data set. The way we say in Pig, X equals to load some file, it means X is a data set which we have just loaded. In the similar fashion, when we start working on Spark, in the beginning we have to load our data into resilience distributed dataset. And what does it mean? It means that your data will be loaded partly into memory, onto multiple disks, multiple machines running Spark. Okay, so you can see here that there is HDFS and you are loading data from HDFS into resilience distributed dataset. And you see that resilience distributed dataset is running on four machines here. You see the partition here represents that there are four machines. Machine 1, 2, 3, 4. Alright. So RDD, resilience distributed dataset, is persisted in the memory, meaning meaning if one application loaded a data set, we can make it available to other applications, such that if there is too much of churning going on of the same data, then multiple systems can utilize it. Also, if so, you can imagine that there are four nodes in Spark which are running parallelly. So all those four nodes will handle a single data set. And imagine one of the node goes down, then the resilience, this particular portion of the resilience dataset will be handled by some other machine. Okay, so some other machine will automatically recover from the node's failure. All right. Now, and this dataset can contain any kind of data. It's not necessarily a particular kind. It can contain any kind of objects. And okay, there is there are basically two kinds of object structure we can put. One is normal array of objects, other is array of key value pairs, okay, where each object is key and the value. And these resilience datasets support two kind of operations. One is called transformation, and other set of operations are called the actions. Okay, going back to the analogy of pig, in pig what we did was we loaded the dataset, and then we ran dataset dot filter, dataset dot for each dataset, and I mean, not dot, but yeah, we operated on our dataset. In the similar way here, the all the operations you can run on our resilience dataset, they are vaguely categorized into two categories. First are called transformations, other are called actions. Okay, so let's say that this file which we were, so first of all, let's launch our Spark. And how do we launch Spark? Somebody quickly. Okay, correct. User lib Spark bin PySpark. Alright, so starting. Now we get the Spark cell. Alright, so this is the cell where yesterday we talked about that you can type your Python code here to create functions, and also this is basically a Python shell where you can actually type anything uh, and get it evaluated immediately. Okay, so let's load our data. Okay, what we are doing here is we are saying there is the extra thing is this sc is our Spark context, is the entry point to Spark. Okay, we are saying lines equals to sc.text file, and we are providing URL. Right now we are providing a URL from HDFS. We could also provide the URL from normal file, or a network file system, or some other input mechanism. Okay, let me repeat. So I think there was some disturbance in the audio. Lines equals to sc.text file. We are basically loading a text file. We are telling Spark that here is my text file, and based on this protocol, the first four correct these first few characters before colon are is the name of the protocol. Okay, and there we go. It has loaded the files into the memory. Okay, now this lines is essentially uh, an RDD. It will tell you that it's an RDD here. You can see that. All right. So the next is, once we have this, what we can do is, all right. So Srinivas is saying loading data from HDFS into RDD at Spark side. Data nodes coming. Yes, that's correct. So these Spark nodes running the RDD will be communicating with HDFS and will be loading the data. So we have successfully loaded it. Now we will do, so what this statement means is we have called a function called text file on the object called sc, which was provided to us as it was told Spark context available as sc. And now in this we said that please load our text file, and whatever object it returned, this basically returned an object, and we have saved it into lines. Okay, for demo purposes, for another testing purposes, instead of loading a file, you can convert a normal array into resilience dataset, okay, by using parallelize. So you can say my array equals to sc dot parallelize, okay, and you can specify whatever array you want to specify, okay. So what did it do? It converted this array 1 3 5 6 9 12 11 into a resilience dataset. So if it is distributed, then few elements will be in one Spark node, and few elements will be another, few elements will be in another. Okay. So this my array is basically a Spark, okay, Spark resilience dataset. Make sense? Now next is the kind of operations we can do on lines or my array are categorized into two broad categories. One is called transformations. What happens in all the transformations is that whenever we launch a transformation, okay, it happens on each individual node. Also note that the process of transformation does not start until an action happens. The moment an action happens, transformation is run on the node where is the data, and whatever that it returns, it creates another resilience data set. Okay, and therefore there is no transfer cost between one due to a transformation, because the data produced by a transformation is also stored in another RDD, and hence there would be no transformation cost. Make sense to you? No? So you can see here what we are doing is there is an RDD. We There is a Spark driver application, the command prompt we are talking about. This is where our program is launched onto. So from here we loaded our RDD, and from here we launched transformation. Transformation will transform this RDD into another RDD. Okay, but it does not modify the existing RDD. It will basically create another RDD. Okay. So Manish's question is RDD will be spread across different data node. Is this correct? So RDD will be spread across different nodes, not guaranteed to be data node. It all depends on which nodes we are running Spark. Okay, if we are running Spark parallelly on all the data nodes, then this will be spread across data nodes. All right, good. So Anand, before moving forward, yeah, which part you want me to explain again? Yeah, there might still be a network transfer. That's correct, Manish. But it would try to minimize the transfer as much as it can. All right, sounds good. Great. If you have any questions right now, please raise it. I will try to answer it. So a transformation will be kind of square each element. So any kind of transformation you can do. Okay, it can be based on your complex logic. Okay, it can be it the transformation you will be doing will be based on your complex logic. Okay, so imagine this. So what we are doing here, we are so in the first one. All right. So again, let me. So we closed it. So we launched this earlier. It basically loaded our full text file into lines, and lines contain the resilience dataset. Okay. Now, if you want to peek into lines, we can say lines dot what was that? Take 10. So take is a command of Spark, which basically gives you few elements from the data set. Now you can see that it basically is an array. So you can see that it has returned us an array of first 10 lines of this file. Okay, it's the same file which we used for our word count. This file is nothing but a text file. This file is nothing but the text file containing containing Sherlock Holmes novels. Okay, all the books by Sherlock Holmes concatenated together. I've kept it in this file, and when we load it into our Spark, it basically created a big array where each element of the array is line from the from this text file. Okay, now from this and to see what's there in this, we said lines dot take 10. It went to the nodes containing those lines and fetched us those 10 lines from this resilience dataset. Sounds good to you? Now Manish's point is that so the transformation will be on the similar lines of MapReduce. Exactly. You are thinking in the right direction. And Srinivas is saying line is stateful. Yes. Line is maintaining these details. Lines is the resilience dataset. And resilience dataset knows internally the internal details of lines contain on which machines line exists, and if machine goes down, the lines will spread to another dataset, another machine, and so on. All right. So all of you are on the same page. So also the transformed data is in memory. Yes. So partly by default it's in memory. If we want, we can persist it. There are options to persisting it into the disk. We call them spilling over. All right. And the reason why the reason that it's in memory is for the performance reasons. So you can see that lines.take is returning 10. All right. Now let's do some operation on this array. Okay. If you break it down, if you look at it closely, what do we have here? Lines is this. Okay. Lines is this. It looks awkward. So if in Python, you put a u before the string. From here to here is a string, and you're putting u to mark it that it's a Unicode. Sorry, it's a UTF-8. Okay, and so this is the first line, then this is the second line, and then this is the third line. Okay, this is the fourth line, and so on. All right. So this is for top 10 elements, first 10 elements of our array. Now let's do something. Let's try to run a transformation on the top of it. So the most common transformation is our map function. Okay. So this map is, for time being, let's not confuse this map with our usual map reduce map, usual Hadoop's map reduce map. Let's just think about this map in a different manner. Okay. So whatever we pass as a function, what it is going to do is it is going to apply that function on each element of the array. So if we say our function is define, let's say our function is line length, all right, or we call it line, or we can call it length sg, okay, just to avoid confusion with anything. And we pass it any line, and this one returns the length of the line. Okay, so length is a function provided by Python, and this is how we create the Python function. So we are just trying to create a very simple our own function like this. We could also write more complex logic such as line dot strip, meaning remove all the new lines, or line dot we also replace spaces with nothing. So we could do complex logic here before computing the length, whatever is our requirement. Okay, so here we have just written a very basic function. What it does is whatever you pass to it, it computes the length of that and returns. All right, so this is a line length sg is our function, and anything you give to it, it will compute the length of this one. Sounds good? Sounds simple? Next is let's apply length sg function on the full array. Okay, how do we do that? We say lines, which is our RDD. We say lines dot map, and then we pass the function name. Okay, this is like passing the function pointer. Internally internally this map function is going to apply your function on each element of lines, meaning it is going to take length sg and run it on zeroth element of lines, first element of lines, second element of lines, and whatever values are being returned by your function creates another array which is returned here. Okay, so here what ll would have, what is it that ll would have? Lengths of each line, correct. So basically we take another function, we take a function, and all it does is it will apply first, it will run your length function against first element, then second element, then third element, and so on. And whatever is the result of your function, it will be added to a new array. A new array will be created, and these results will be stored in that array. Now when I say array, it essentially is a resilience dataset. So on a resilience dataset we are applying a function one element at a time, and whatever is the result of a function is creating another RDD, and those RDDs basically will have equal length as the original lines. So the length of lines and length of R LL is going to be, okay. So let me just run this. So if I say lines dot count, it will return us total number of elements in lines. All right. Now also note that When we ran this function, map function, it took a fraction of seconds and got it done. But the moment we said, uh, but the moment we said lines.count, then it's taking time. You see that? It's taking time, meaning the real execution is happening now. When we said lines.count, it it is going to execute. It is going to execute all of this. First, it will read the data, then it will run your map function, and then it will do the count. Okay? And in case, yeah. So now it has printed us these many lines. Okay? Now it has printed us these many lines. All right? Now next is, okay, next step in the case is let's compute the ll.count. What will ll.count have? How many will be ll.count? Yeah. What will be the result of? Correct. Okay. So you can see that. You can see that it has also returned same. Perfect. Is everybody clear on the transformations part? So we had a data which we loaded into RDD. RDD means array distributed over multiple machines. And then we applied a function on top of array. So this paradigm, if you look at this line number 9 is something which we are not very used to, because this comes from functional programming language, where we take a function, we run it against the data. All right. As a matter of fact, map, reduce, filter, all of these functions come from functional programming language, and are a very well known in the functional programming area. Okay, so here we are taking the code, this particular code from line number 5 and 6, and running it all across the cluster. Okay, so there is no second transformation, Srinivas. So far there is only one transformation happening. Manish is clarifying something. He says that transformation equals to one RDD to another RDD to another RDD till get the results. So yeah, one transformation means one RDD to another RDD. Okay, like this one is a transformation. Line number 9 is a transformation. Okay, so Manish's point is, so for example, the file is very large. It can't load the entire file into memory based on combined capacity. How so? Spark calls it spilling over. If it can't load into the memory, it keeps some part into the disk. All right. So here the main concept I'm trying to run. Okay. Then map is just one transformation, a function that transforms one value to another. There is another transformation called filter. Filter will transform your RDD into another RDD, and will basically put the elements from the previous RDD to the next one if they are qualifying your function. So let's say we want to put only lines out of LL, we want to put only the lines which are which are of greater than 0 length. Okay, so in those cases what will you do is you will say, so right now is element is equal to the line, element of the So in case of lines, each element is a in case of this RDD called lines, each element is a single line. Okay. In case of LL is also another RDD. Each element is the length of each line. Correct? Because that's what is computed by a function. Now let's go ahead and create another function. Let's say f equals to. So what we are trying to just tell me what should we do with. So on LL we can apply another transformation and we can say LL dot filter. So yes, that is configurable, Manish. That's a good point. So while you are loading, right? While you are loading a file based on what you supply here, whether text file, binary file, based on that, the loading happens. Okay. There are many other functions in SC to load various different kind of format, and also you can supply your own format just like the way we provided input split format. In the similar manner, it also accepts a transform the way you can load it. Okay, is that what you're looking for, Manish? Here, since we are supplying it, we are telling that here is my text file, so sc.text file will load the data. All right, good. So now let's try to apply another function called filter. This is also transformation. It will transform our line length using, let's say we only want line lengths which are even. Okay, so all we need to do in this case is we say ll dot filter, and we also write a function called is even. What does is even do? Whatever number you pass to even, it will return true or false. Okay, so x divided by 2, if the remainder is 0, then 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 it returns true, otherwise it returns false. Okay, we pass is even here, and that means we'll get ll even, only the line lengths which are even. Okay, let me show you the impact of this function. So is even, and we say 0, it says true. If we say 10, it says true. We say 101, it says false. Okay, sounds good to you? So you can see that, I mean, negative numbers is not something which we have handled so far. Okay, so is even function we have just written. Now we are saying transform LL. Okay, transform this RDD into LL even by applying a filter function and using is even as the argument. What does it mean? It will take your is even function, will apply on LL's element. Now let's say LL dot take 10, LL dot take 10. It gave you these first 10 record. So okay, 64 will go in the output, while 25 will not, 45 will not, 0 will go in the output, 68 will go, 68 will go, 42 will go, and so on. So all these elements, so these are just first 10 element of LL. There are quite a few elements in LL. There are basically 1, 2, 8, 4, 5, 7 elements in LL. Now we want to just pick few of them and put it in LL even. Okay. Now you can see LL even has, we can say take and 10. Now you can see that only the even numbers have come into the newer data set. Sounds good to you? So that's another kind of transformation called filter. Map puts all the elements from the input after passing them through your function into the output. Okay, map basically takes a function, applies on each element, whatever is the result, creates another array and puts all these results into that array. Filter only puts those elements which qualify, which basically for which your function says that let them go. Okay, so your function is checked against each element. If your function is saying that let this element be put into the output by returning true, then the element will be put in the output. If your function returns false, which means that element should not be put in the output, then that will be ignored. So question to you is that, okay, so let me ask you this way. So now we have ll even, right? If I say ll even dot count, will it be ll even dot count will be lesser than equal to ll dot count? Is this statement true? Yeah. Baswaraj? Okay. All right. So basically what we are saying is we are applying a filter function. Okay. So again, we loaded lines using Spark, and then we applied a map function on lines. Okay. Uh, what does it mean by applying function? Taking a function, applying, running this function on each element of array, and whatever is the result, you put it in another array. Which means for each element array, for each element of lines, you will have an element in LL. Okay. Now for each element in LL, we ran filter. Okay. For LL, we ran filter, which means that we want to run is even on each. Basically, filter will only put those elements from LL which qualify is even. What does it mean by qualifying is even? It means that for the values for which is even returns true, ll dot ll dot filter will put only those elements into the output. All right. Okay, now the next thing is, the other one is flat map. Flat map basically converts the elements into, so this flat map is equivalent to our map reduce, usual map reduce. Okay, you in the Hadoop, the map reduce was there, for in which each input element can be mapped to zero or more output elements. All right, for each input element, the it will be putting more than one, maybe, or maybe for some it may not be putting the output. All right, that is flat map. So your function can return zero or an array of element rather than a single element. In our this case here, this was our map function which only returned one value. But if you are passing, if you are running flat map against each value, then the flat map can return an array of values. All right. So so let me just see. Okay, so you run flat map, I'll show you use case of flat map while doing the word count. Next transformation is group by key. Okay, group by key means we can specify our elements as tuples, okay, and then group by. Yes, so we can define our element like this. We can define our element in the manner like this is our key and comma value, okay, okay, and then we can put key 2, key 1 like this. So okay, you can see that. This is how you can define your elements, and based on this, if you say group by, it will basically group your data based on this key, the first element in the tuple. This is called a tuple, this square brackets one. Alright, so now let's just go ahead and first try to run. So now in our description, lines contains lines. Now we have to break down each line into a word. So what we need to do, since each element need to return multiple elements, so what we need to do, okay, so we want to break down, so lines contains an array of lines. We want to break down each line into a word. So what will we do? Anyone? Split. Good. So will we use flat map, or something else? So map returns only one value per value. Okay. Flat map returns multiple values for each value. So let's just say define two words. Okay, that's our function. And we pass it a line and we say return line dot split. Okay, that's it. That's our function. This is going to split our line. So two words, and whatever you pass here, we can say, okay, you can see that. Now this is our Python function. All right. Now this Python function is returning an array for an element, and so we can say words equals to lines dot flat map, and then we can say two words. So words dot count, what does it mean? Sorry, not word dot count. Let's say words dot take 10. All right. Let's say that one. Now you can see that now your RDD contains each element as a single word. You can see that. You can see that. All right. Now Srinivas is saying, suppose you want to split with different separator, then we can use, yeah, we can use that one here. Okay. Also, if you want to clean lines here, like lines dot lower, you can say line equals to line dot lower. Okay, we converted line into line dot lower. Then you can write the function in this way. Okay, here. So now if you run this one, what will happen is all the words in the output are going to be in the lowercase. You can see that it is now lowercase. All right. So this is a little important. That is why I'm trying to make it that way. Okay. Also, we want to make it ready. We want to make it ready such that, so here we could also have we could have another function instead of that. We could say, instead of saying this, we could also say two words tuple, two words kv. Let's call it kv. So what will it do? It will first convert the line into lower, and then it will split it. Okay. And here we are putting a loop saying for words in line dot split. Okay. And we are creating an array. Okay. And we are saying array dot append, array dot append. And in this, what we are saying is, or I think a better thing would be, let me not mess up. Let me just do the way we were doing. So now we have words. Okay. Now we want to convert words tuple equals to words dot map to kv. So this k2kv is our function which will convert each value, each string into a key value pair. And how will it do? It will basically put word comma 1. Okay. So we are creating another function which basically converts any array you give it, any array you you, you apply this 2kv on, it will convert it into so 2kv, and we say 2kv and say there is Sandeep here. Okay. So what will it do? It will basically return Sandeep 1. That's all. That's all it does. And what and words has a list of values. So now list of strings. Now what will it do is when we say this, right? So if you remember, words dot take has how many elements? So words dot take has this words dot so first 10 elements of words, 10, top 10. Okay, first 10 elements of words are these, and first 10 elements of words tuple, what will that be? Quickly, will be, okay, correct. So you can see that first 10 elements of this another RDD is this. Okay, just one appended to it and put in the brackets. Now we can apply reduce by key on this. Okay, so we can define a function called let's say, what do you call, uh, okay, so let's say we call it uh, word count, word count, and we are defining a function as word count, and basically we'll get an array here. Okay, in this function will basically call array dot sum on array. Okay, or we can also say things like sum equals 0 for each element on array. It basically sum up each and every value and then returns the sum. Okay, so basically it goes over the array, sums it up and returns it. Okay, word count, and we say 1 comma 2 comma 4, it will basically return the sum. That's all it does. Now let's apply the reduce. So this was our words tuple, right? So on words tuple, we can say words tuple dot reduce by key. Reduce by key is equivalent to group by and then apply the aggregator. Okay. Reduce by key. Key will be the first element, and the second element will be your word count. Will be aggregated together and passed to the word count. Okay. So here there'll be, you know, what do you call, frequency of words. Frequency of words equals to words tuple dot. So now we can say dump, or we can say not dump, that's big. Frequency of words dot dot take 100. Okay. So what does it say? Just a second. All right. I think reduce by key we will discuss after some time. All right. All right. So okay. Okay. So I'm sorry. Here I forgot that I'm dealing with word count does not do sum of an array. It basically sums up on two values. Okay. When we talk about actions, then you will understand this. And so you can ignore this part for time being. So now it will, just like combiner, it will be on. Okay. Just like combiner, so you can see that it has computed the frequencies of the word. All right. All right. So what we did here was we wrote a function called word count. Given two values, it sums it up and puts it into another value. All right. It puts it into another value. That's all it does. Frequencies of words equals to words tuple dot reduce by key, and we have this. So Srinivas's question is it a key or value in the array? So here this is a tuple in this array. Is this what you're, line number 39 is what you're talking about? So this is basically each element is key value pair. Okay. Now last operation is reduce by key. Reduce by key as in if you remember in combiner was called recursively on elements. We'll talk about this. You will get more hang of it better after we discuss a little bit more. Okay. What will be the input to the word count? Word count you will get, the input you will get is the full array. Like, so after we say reduce by key, it means group by key, and the aggregate function is your word count. So you must be expecting that in the word count, it should receive a full array of numbers for each word, and then it should sum it up. Okay. Instead of that, your function is applied recursively on the values. All right. I'll show you that. So for time being, you can assume that word count takes two elements, and using these two, so if Spark has to sum up an array of values using your word count functions, so what it will do is it will apply your word count function again and again until it reaches a single value. Okay. So reduce by key, what does it do is, first it groups this full array, it groups this full array by the key. The first element in this tuple, in the tuple means basically something in the round brackets, and this is the behavior is similar to the square array. So in this sort of an array, the first element is considered as the key and the second element is the value. Now reduce by key, all it does is it first groups by the first element of this tuple, and after grouping it, all the values that are accumulated together, those are aggregated, those are summed up, those are aggregated using your function. Yes, reduce by key is part of an RDD, resilience distributed data sets definition. Yes, it's a part of Spark. Okay, so this way we computed the word count, all right, word count in the text file. All right, so before we move forward, I would like to describe a little bit more. So those were transformations. Now actions. Actions means, so reduce by key is not strictly a transformation, it's actually an action, partly an action. Now so in case of transformation, we were computing some values from existing RDD and putting it back into RDD. But and that was not executing until we said take, or until we said something like sum or count. Okay. Until we said count or until we said take, it did not do anything. Similarly, when you used pig, until you say until you say dump, or till the point you say store, it will not do anything. It will just keep on noting down that the user has asked for this kind of a translation. All right. Now the actual work starts happening when you call an action. And what does it mean by an action? Action basically brings the data back to the place where you started, the command prompt or the launcher box from where you are launching your script. So action basically converts the full array into single value, or action basically converts an RDD into our normal variable. Okay. The way sc.parallelize or sc.text file converted our converted our uh, text or our file or our normal variable into an RDD, action does the reverse. It converts the RDD back to the normal variable into the memory of the driver application. Wherever we are launching the driver application, the variables will get loaded into that machine's memory. All right. So that is an action. All right. So there are multiple kinds of actions such as reduce. So if we want to, so we had LL, right? Yep. So I will try to explain it in a different terms. Okay. So let's say we have we are loading LL is there, right? We want to compute the sum of all lines. We want to compute sum of all lines. All we'll do is we will define a function called sum, note the capital, and we will return x plus y. This is our sum function. Okay. We can say sum 1 comma 3, and this basically computes it quickly. Okay. So in very simple word, while transformation created an RDD from one RDD, an action converts an RDD into a normal variable, which means it takes the data from RDD, gathers it at the user end. All right. An action is something which make things happen. Transformation is just noted down by Spark in a lazy manner that whenever an action will happen, then we will think about it. Just like the way Pig behaved. Pig also took a list of things from you, like in Pig we applied filter for each, this, that, but until we say store or dump, it doesn't do anything. In the same manner, until you launch an action. So far we have been able to demo you things because we were calling silently actions such as count and such as take. Okay. Yeah. Transformation is nothing but execution of your custom functions. Okay. So now if the important thing to note here is that when we call sum, okay, it takes only two values, but if you remember, let me just create, let me have ll dot, ll has the line length, right? Now I want to count total length equals to ll. So what was our name of the, yeah, here it was, yeah, ll was our length, line length. Now we want to sum up all the line lengths, so all we need to do is ll dot reduce, and we pass our sum function. Now you can see that it has done the computation, and where did it keep it? I need to figure that out. Where is it getting lost in this? Oh, we are not, yeah, we are not printing. We need to say total length. Now you can see that it has computed the total length of our file. And what did we have in ll? ll dot take 10. First, these are first 10 elements. These are this, okay? Clear? Not clear? Or let me try to create another array. So let's say this is my array. This is my array. Let me just create this array. Okay. Now I want to do something nice with this. I want to say that I want to compute the this the maximum of this one. Okay. So we define a function called max. Let me say max. I'm putting it capital so that because there is a similar function in Python. So max will return bigger value, okay, of x and y. If x is greater than y, then return x, return y. Okay. So max will basically whatever value you give, it will give us the bigger of the two. You can see that. Now let's apply this reduce function on our array. But before we can apply anything on the array, we can say array rdd equals to sc dot parallelize and we say array. Note that we, instead of saying text file, this time we have called parallelize. Parallelize is the one which can convert our normal array into an RDD. Okay. Now we can call on RDD a function called max by using through an action called reduce. Reduce is an action here. Okay. And we can call max on this. Okay. Now you can see the answer is 68. Correct? And answer is 68. So technically we will have one action in a Spark script, or in other words you can do one to one multiple transformation, but eventually there will be one action. Yeah. That is correct. So what will happen is, in the beginning, you will load data into RDD. You will do various kinds of transformations, maybe filter, maybe map, maybe flat map, maybe there are all other list of transformations. And once all of those are done, you will call an action and bring the value back. And if you want to further do a processing, if you want to if you realize that you want to merge this data with another data and load it again in RDD, you can do that again. All right. All right. So the other reduce functions like count, okay, count, take, we have already covered. Okay. And there is another function called collect, which basically gathers all the elements instead of only few element. Okay. So other than these, there are more, such as first, meaning first element from your RDD, take sample, meaning if you want to just like sample command of pig, in which you want to pick up only few elements from the full sample. And take ordered, as in the way they are stored, sorted way. And save as text file, this will save our data into text file. Okay. So everybody clear on transformation and actions? So the important part with respect to reduce function, reduce action is that whatever function you pass, it will be applied recursively on the values. Okay, let's take a look at this example. So we had these examples, right? This one. Okay, this is our example, and we applied a max function on top of it. Okay, so we were applying, there is this array called here. You have an array. Now what we were doing is we were applying our max function. Max function basically takes two values, x and y, returns maximum. So first max will be applied on these two. Okay, let me just create. Okay, so this array, the new array after transformation. So what, when max applies on this, what will be the result? Quickly. 64. Then next to 45. So I mean, okay, be careful. Actually, I'll do exactly the way Spark does. Spark starts from the rightmost. Okay. So first 68, then 42 and 0. Correct. So 64. What was that? So here 42, then 68, then 45, then 25. No, not 25. So 42, 68, 45 and 64. Okay. Now again the same max function will be applied on this. Now the value will be from the right hand side. Okay. it will be 68, and then you have 68 again, and then you have 64. I don't know, but there must be reason. But this is what I've noticed, so I'm doing it in the same way. Because if I give you an example of, okay, so now this will become 68, right? And in the next pass, it will be 68. Now you can see that it has slowly applied your max function multiple times to reach to a value. And in MapReduce, what was that function which happened in the same way? In our Hadoop, when we were studying Hadoop, what was that function which behaved in the same way? Correct, the combiner. So we recursively apply a function until we reach to a singular value. All right, and this is a common concept in so this function, whatever you are writing, whatever reduce function you are writing, it has to be cumulative and associative. Okay, I can give you a demo right away. Then how does, so let's take a case of our array. So I'll write this code for you. Okay, so let's say there is an array equal to 1, 1, 2, and 5 and 7. Okay, and we loaded it, then we defined an average function. Okay, what average does is return x plus y, returns x plus y divided by 2.0. Now, if we say my total average is arrrdd dot reduce, and we pass the average function, do you think we will get the correct value? So this average of this is 15 by 4, right? The average is 15 by 4, correct? Ideally, we should get the same result here, but we will not get the same result here. So we load this, okay? We created an array, we parallelized it, converted into RDD, and then we created a function which basically computes average. So we can test our average function. Average function is working fine. No, this is not correct. Average function is not working fine. We need to put brackets here. So good part about the interpreter is that we get results very quickly. Now let's apply the reduce function and see what happens. Okay, so it says it has put the value in a. You can see that, okay, we are actually lucky in this sense. I think this will be better. We don't need to define the function again. Oh, we are again lucky. So 15 by 4 is how much? 3.75. We are actually just getting lucky here. let it finish. Now you can see that now it is how much. So we can also compute array dot sum divide sum of array divided by length of array. So is that it? Yeah. So if you can see that for this array, when we applied the average, right, the value was 3.84. Okay. While the true one is 20 by 5. Okay. Here the result was 3.875. Correct. So the functions like average are not really great for reduce. Okay, you cannot compute average using the reduce. So Anand, those are the limitations we are exactly talking about. All right, so everybody convinced about it? So I wanted to give you the demo of what we even studied during combiner. So you just saw that when we applied the average function recursively, we got 3.875, while in 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 true sense it should have been just 4. No? Convinced? No? So what we did was we created an array, we loaded it, converted into an RDD, we created our own function to compute average, and then we did reduce here. Okay, on this we run the reduce such that this average function will be applied recursively on the full array, and whatever is the result comes out. Yeah, sounds good to you? So here it's not, I mean, it would actually show you various kind of tasks. Okay, so but be assured that for these 1, 2, okay, then 3, 4 and 5, total number of 5 times our average function is going to be called. We can print it here. I think we can say things like this, and let's see, let's hope that it prints here. Okay, so you can see that xx is being printed multiple times. So let me, yeah, so here you can see, I'll just grab in this text, then it'll be better. Let me just find out how many times xx was called. You can see 1, 2, 3, 4. 4 times it has been called, not 5 times. Interesting. So let me just count. Okay. So to convert it into, say, uh, for this one, okay, for this one, 1, then this, and then nothing was called. Okay. So that was x1, and so 2 times I've already called. Okay. 2 times. 2 times have been called. Now 3 times. Now 4 times. Yeah. So basically total number of 4 times is called. So this is correct. Okay. By printing we just quickly computed how many times it's being called. So alright, so should I move ahead with the actions, because this is probably the very important part. Alright. Now the next one is the shared memory. Okay, next one is shared memory, in which various tasks like your mappers and reducers, say we are running mappers and we want to communicate continuously, then we can use broadcast variables. These broadcast variables will be made available, and just to keep everything in sync. So when you are launching any of your function is getting executed multiple times parallelly, whether it's reduce or whether it maps. Based on how many RDD nodes you have, your function will get executed parallelly. Okay, so all right. So basically, whenever we are using the broadcast variables, so we can communicate with between multiple nodes. Okay, so on one machine is your map function running, another map function is running, and if they want to communicate they can broadcast. And the way broadcast works is you start with a broadcast, with a simple broadcast, and this broadcast variable will be available to your function, and in this you can keep on writing the things, and you can keep on informing each other using the broadcast variable. All right, so you can say broadcast dot value, and then you can start. Okay, and we can read from a broadcast variable and write to the broadcast variable. The way it happens is when you try to change, when any of these nodes try to change, that if they try to change, then it will basically inform all other nodes that that there is particular node who is trying to modify, this broadcast variable, and therefore others will wait till the broadcast completes. Okay, so the broadcast is actually extremely fast. The other way of coordinating is using accumulators. Using accumulators, as in all the Spark applications will keep on sending the data to the counters and accumulate. Okay, so the data from RDD is coming to the accumulators. So whenever you have a unidirectional output like sysout, or every node is just giving out counters, in all those cases you use accumulator, just one way. Okay, just for gather the data from all the nodes, we can use accumulators. All right, now the word count example which we have already covered, you can also have a look at it. This is the way we had covered. So we loaded the lines, we defined a function which would split our line into words. So we okay, so okay, so then here we splitted the line into words using flat map. Okay, flat map, because one element is resulting in multiple elements, that's why we are using flat map. And then we basically converted each individual word into a tuple of word comma one. Okay, the key value part, and then we used map function for applying this on each word. After that we just reduced by the key, and we got the result here. And the other important aspect is we can save any of the RDD. Any of the RDD we can directly save onto the disk. Okay, sounds good. Everybody okay with this? Now, the assignment for all of you is using accumulators and broadcast, modify this example and run it by yourself. Okay? All right. So Yeah, there are other formats also. You can have a look at the Spark library to understand what all other formats it supports. Okay. Okay. So let's take a 10 minutes break. Back by at 8:42 a.m. IST. So, hello everybody. Should we start now? Yeah. So you haven't come back yet. Yes. So are you able to hear me? All right, then let's start. So we talked about Spark in the first half, and there we basically used Spark for computation, and we created RDD. And RDDs are pretty fast because they utilize memory and tries to do things in the memory so that so every operation is blazingly fast. So few people realize that if few people realize that since the RDD is extremely fast, maybe we can use the RDD for streaming. Okay, as the data comes in, we will keep putting the data into RDD and we'll keep on reading the data from RDD. Okay, and that's when they realize that we can actually use Spark very well for stream processing. What does it mean by stream processing? Stream processing means that the data coming at a very fast speed, we can process it by converting the incoming data into windows as in a window of size something, or you can say a small buffer. Instead of c- processing each element, we always process a bunch of elements together. And that is the whole philosophy all stream processing methodologies follow. Okay. So again, in stream processing, we read the data from resources which are generating the data at a very fast pace, such as Kafka, Flume, HDFS, 0MQ, Twitter. The other thing is in the Spark, these streaming applications, all streaming applications almost keep running in the background for quite some time. Okay, though they run in the background for quite some time, but they process the data as and when it arrives. And after processing the data, they put the data into HDFS databases or maybe the dashboards. Okay, so okay, I'll give you an example of stream processing. So I was handling the detail page at Amazon where my role was to optimize the image and do the image selection in case of a detail page. Detail page is the page from which you buy the items in Amazon. There is an image on the left hand side. So my the objective of the project was to optimize that image in a really fast manner. Now, sounds actually pretty straightforward, but now consider this. Every second, there are changes in the pages. There are vendors who keep on changing the page, posting various kinds of data, and posting all the images, and there are lots of other information they keep on posting. And this image selection optimization depends on every change the vendor is making. If they are changing the title, if they are modifying something else, even if it has nothing to do with the image, still it does impact the image selection. So therefore, as and when the users modified, as and when the vendors pushed more data, the we had to continuously keep changing the image. So what am I trying to say here is that continuously, every second, there are around ten updates from the various vendors for each product,
for various products, and those updates need to be applied on the image. So, and this is not a, one time process. It keeps happening all the time. We have to continuously waiting for the data to arrive, the changes to arrive from the user, create small windows of the data, create say 10 records per window, and then process that window and put it in the databases and update our database from which the detail page will be served. Okay, so that was an example of stream processing. The other examples are, say you are downloading data from Twitter and continuously you want to keep computing that who is trending at Twitter. Okay, so your job is to just publish who is trending on Twitter. So all you need, instead of using Twitter's way of trending, we say implement a new way of trending. So what we will do is we'll create a program which will continuously read data from Twitter and then push it to push it to our website or somewhere. Okay, so these are few example of Spark streaming. It's an extension of the core Spark API because it has high throughput and fault tolerance. Therefore, it is suitable for streaming. Okay, it's not equal to Hadoop streaming or something, because in Hadoop streaming, there streaming means running some external command on data. Here, streaming means the data is actually being streamed. Okay, and also it's not video streaming. In video streaming, it's about playing the video to the user, although under the hood, a data is being streamed from the server to you. All right. So in case of Spark streaming, we convert the data, input stream of data, into the batches of input data. And we give that batches of the input data to Spark engine that will process it by running our code and output the batches of output data. All right. So workflow is Spark streaming receives live input data stream. Okay. Then since none of the applications in the world, none of the stream processing applications in the world handle the data as and when it comes. They all form a small batch and that and then apply the logic on that small batch. Okay. So you can see that internally, so the core of Spark streaming is something called D stream, and D stream means discretized stream. Basically, it converts the input data which is continuously coming into the batches. Okay, batches means the RDD at time 1. So a D stream will be represented as RDD. Okay, so data from time 0 to 1 will be one element. Data from time 1 to time 2 will be another element in this RDD, and data from time 3 to time 2 to time 3 will be another RDD, and so on. So we will be this way we will be creating an RDD out of the continuous stream of data, and this is done using a stream, basically a programming construct, a class called dstream. Okay, so the Windows operation, before we understand the streaming function, we basically need to understand that we create windows on input data. Now imagine this original stream is coming at time 1, time 2, time 3, time 4. Okay, and we are creating the windows of the data, window at time 1, window at time 3, and window at time 5. So window at time 1 will contain maybe nothing, while window at time 3 will contain time 1 plus time 2 plus time 3. And similarly, window at time 5 will contain 3, 4, 5. So sometimes when we are doing stream processing, we would like to process an element twice rather than missing out an element. Okay. Now, on top of this D stream is nothing but input data converted into an RDD, where each element in the input data is for a period. Okay. So on this input data, we can apply various kinds of transformations and reduce transformations and actions. Okay, and also provide some one more parameter called per window. Okay, so we can say pairs dot reduce by key and the window. Okay, we can say that for this window only, please compute the MapReduce. Okay, so these are the programming constructs provided by Spark Streaming. Now I'll just take you through this example of computing words per minute. So in every minute, whatever words are being received continuously. So concept of window is pretty straightforward, Manish. So we read from the data. Okay, so when the data is being written by the user, we'll keep on reading it. As soon as we finish reading, say 500 elements, we'll create a single element, push it into the Spark, and then start reading further. That's the role of, that's how it happens. Okay, so we create window on timeline. Instead of handling it per millisecond, we start saying our, say your data might be coming at per millisecond, right? 10 record per millisecond. So per second you will have 10,000 records. So a window of 1 second will have 10,000 records to handle at a time. Okay, so that way that's how you basically reduce your headache. If you try to execute on per element basis, then you will not be able to actually handle streaming jobs. Let's I'll just take you through this service. In this service, basically we are creating a network uh, daemon, which a service which basically has a window of 1 second, 1000 millisecond, window of 1 second, and we are reading the data from the a particular socket. We are reading the data which is being received at 9999 port, and we are reading continuously into lines. Okay. Also note that this is kind of a Java kind of a code, because in real life when you are doing streaming, most likely you are trying to build a service, and people prefer service in Java, and that is why I have mentioned it in Java. So it should not be a problem to you. Here, what we are trying to say is we are creating a Java streaming context object. We are sort of calling the constructor. We are constructing a streaming object by specifying the name for this process, and also we are specifying how big the window should be. All right. After that, we are saying that read the data from particular host, listen to the data, sorry, read the data from particular host and particular port, and represent it as lines. Okay. Lines is a RDD. Okay. Lines is an RDD containing the strings of the data that is coming and per second. Okay. Each line is the data which has been received in a second's time. Now, on top of these lines which we have just received, we can call flat map kind of a thing, what we had done earlier. Okay. Similar to the way we had done earlier, we could basically split it into words and return it. And after that, we can do like prepare the tuple by converting into S1, and Afterwards, we can basically apply reduce by key exactly the way we had done. Now, these step number 2 and step number 3 is exactly the way we had done. The most important part here is this construct. Instead of creating a normal RDD, we are asking our D stream to create the RDD for us. So what is D stream doing? Is reading the data from localhost at this port, pushing it into Spark, creating the RDD on top of that data, and then giving you the control of that one. Now you are able to call your flat map or map function to convert it into tuple, and then reduce function happily, and afterwards you can call collect, and the there you have the full your usual Spark application. Okay, so thereby for each set of lines from 0 to 1, your flat map operations is going to return the counts of words in each window. Okay, so Apache Storm. Okay, so I hope this is clear to you. So for each second of the data, we were able to compute our frequencies. We are computing the word frequencies in the words received per second. Sounds good? No? So do we also have a concept of window in Flume? No, they don't have that concept. The window is enforced by our buffer. Okay, so you can think of the buffer as your window, and as the data is being read from the source, we are putting it into this buffer. We call it channel, right? So channel behaves like a window, and we take this full window, push it to the disk. So although there is a concept, but there these Flume agents are not singular. They are all pushing it to the central machine, and they are not letting you execute your code so seamlessly. Okay, all right. So those are the few things we can look at. Right? But Flume is not really suitable for the streaming. But Flume does push a lot of data at a very fast pace to the our SDFS. But we can think of actually some solution where Flume can be utilized for parallel execution of things. All right? Sounds good. Anand, Basraj, Lakshmikant, Manish, Pravita, Srinivas, Surya. Everybody okay? Should we move? All right. All right. Great. Great. Now, moving on here. Okay, so the similar task is done by Apache Storm. What we just showed you was a streaming wave using Spark, but for years we have been using Storm, Apache Storm for the same kind of a work. Okay, so Apache Storm is a distributed real-time computation system similar to Spark streaming, and it reliably processes unbounded stream of data and can be used with any language. It's really fast, a benchmark of greater than 1 million tuple per second per node, is highly scalable and is fault tolerant. It guarantees that your data will be processed. integrates with the queuing and database technologies. All right. It integrates with queuing and database technologies. And all right. So theoretically, the Apache Storm is actually used in very real-time analytics. It's used in online machine learning, continuous computation, distributed RPC, ETL, and lots of companies are using Apache Storm. Now, when we compare Apache Storm versus Spark Streaming, we we have these comparisons in place. So the processing model is one record at a time, while in case of Spark, we have mini batches. The latency in case of Storm is sub-second, and in case of Spark, we have few seconds. Okay, so in case of a Storm, because Storm has been designed bottom up for doing the stream processing, you also install Storm on hundreds of machines parallelly, and then these machines process the data parallelly. Okay, in case of Spark, the you only process the data exactly once, but in case of Storm, you would like to process the data more than once, because it's better not to miss the record than process it twice. Okay, the programming model and programming API in case of Storm is the one is backtype. So Storm was created at Twitter at the time when the Twitter was not Twitter, it was backtype, and Spark was created at Berkeley. All right. So Storm is written in Closure while Spark is written in Scala, and API for Storm is available in Java, and for Spark, Java, Scala, Python, everything is available now. All right. So also, Spark is a model which not only does Storm, but does not only does stream processing, but does a lot of other things. And for if you already have a Spark running, it doesn't take anything at all to use that Spark for streaming, because Spark streaming is nothing but a library, or you can say that it's an additional Java program. It's not a service. It's not something you will dedicate more memory to. Okay. So if you are already consuming resource by running the Spark, you can utilize it that way. So in very simple words, Storm is is faster when it comes to stream processing, and Storm is has been for quite some time, has been proven well. But for Storm, you will have to again install multiple machines to in order to get things done, right? So if you already have Hadoop installation and you are running your Spark on top of it, you don't generally need to install this Storm and other things. You can get your stream processing done over Spark itself. All right. You can see the further differences by reading through these blogs. Now, I will like to take you through quickly through various solutions available in case of the NoSQL words, because the general challenge which every one of us will face is whether to use this or use that, whether to use this database or that database. Okay, so the easiest way to decide is first quickly build up the mental map of what are the various solutions available, and then going the deep dive after you have figured out the the three or four databases which satisfy your need. Then you go into the deep dive and compare the results. Okay, so deep dive you will have to do it by yourself, but I can help you in building the quick mental map of these NoSQL servers. So, I just explained to you the difference between Spark and Storm. So the conclusion was, if you don't have anything and you are okay to dedicate so many machines, then then you can use Storm. If you already have a Hadoop cluster and don't want to dedicate more machine, then you can use Spark. Okay, it's as simple as that. Also, the in case of Storm, your latency will be less than a second. Here, it will be greater than or equal to a second in case of Spark. All right, that was a quick difference. Now let's talk about another database like the way we have HBase. There is a database called NoSQL. There is a database called Redis. What is Redis is it's an in-memory database. Although it every data which is in the memory is saved onto the disk, but but almost all of the data, not almost, but all of the data is in the memory, and it runs parallelly on multiple machines. Okay, so whenever you use in-memory databases, they are extremely fast, but as you can imagine, they are extremely fast and they can handle very complex objects. Okay, a complex relationship between objects can be handled in memory, but but these databases, the only limitation they have is they cannot handle too much of data because typical size of RAM is quite low. Our computers has 8 GB or 4 GB RAM, but on the server side you can at most acquire a 200 GB RAM machine, which is really highly costly. Okay, so quick point is that you use Redis kind of an in-memory database when you handle a rapidly changing data. Other thing to note about most of the disk-based systems is writing to the disk, whether it's SSD or normal hard drive, is extremely slow. So whenever you have a rapidly changing data with very small size of database, okay, that should fit mostly in the memory, maybe multiple machines, but it should fit into the memory. Okay, so the examples could be for Redis. Examples could be real-time stock pricing, real-time analytics, leaderboards, and real-time communication. And whenever you use Memcached before, if you have used Memcached, has anybody used or heard about Memcached? Okay, so Manish, that's what we are discussing now. I mean, Manish's question is, so how one decide one versus another? So first thing is, the first question you might ask is when to use MapReduce and when to use Spark. The answer is simple. Whenever you are dealing with terabytes of data, or maybe more than terabytes of data, then you should prefer MapReduce. If it is less than terabytes of data, you prefer the Yarn. Okay, because Yarn performs really great when the data is something which is fitting well into the memory. Not sorry. Spark is something which handles well. Yeah, yeah. Sorry, sorry, Manish. So yeah, so Spark is something which you use when the data is less than 1 TB, so that it can be handled in parallelly, maybe hundreds of machines, and we should be able to handle it in memory. But the moment the data goes far beyond the memory, then you should prefer Spark. You should prefer MapReduce over Spark. Okay, that's a quick comparison. Second, in the similar cases, Storm versus Spark, if you already have the full Hadoop stack and you are okay to with a latency of a second, then you should go for Spark streaming over Storm. Otherwise, if you are not okay with 1 second, you might have to purchase more hardware and might have to set up the storm on your cluster. Okay. And when you are doing rapid changing data, meaning you are changing the data very frequently and you're updating it, and you don't want to compromise in the speed at which you want to process the data, you should go for Redis if the size is smaller. Okay. Now, when do you use MongoDB? MongoDB is good if you prefer to define indexes, if you have indexes on the data. Okay. So MongoDB is not in memory. Okay. But it also utilizes memory whenever required. And MongoDB tries to give you a store in which you can store JSON kind of a object. You can see on the right hand side. So each row in MongoDB is a JSON object. Okay. And it also provides you indexing on various variable, the field names such as first name, last name, age, and address dot street address. It allows you to create indexes on those parameters of an object so that you can quickly look up those objects. So, okay, if you need to do a lot of dynamic querying, and if you prefer to define indexes, not MapReduce function, and if you need good performance on big data, and okay, also if you wanted CouchDB also does the similar thing, but your data it changes too much and filling up the disk. In all those cases, MongoDB does really well. Okay. So most of the things you were doing with MySQL or Postgres, but having predefined columns really holds you back. In all those circumstances, you can have MongoDB. So one object in one row can have different parameters in the second object in the second row. Okay. So one row can have an object which may not have some field, and other object may have some other fields and may not have some fields. So all objects are not bound to have the same set of fields. Now there is Cassandra. Okay, when you need to store the data so huge that it does not fit on server, but you still want a friendly, familiar interface. So Cassandra is good. Cassandra and HBase is a tie. Okay, Cassandra provides you a really nice SQL kind of a interface where you can write queries, you can write all sorts of things, and it gives you data quickly. So basically, whenever you are having Cassandra, you can query the data quickly using an SQL. It provides you a SQL kind of interface. But okay, so whenever there is a too much of data which you cannot handle so easily on few machines, you need hundreds of machines. In all those cases, you would need Cassandra. Or now Cassandra and HBase are sort of our competitors. Okay, Cassandra and HBase, we and reason is that both provides you tabular structure. MongoDB did not provide you tabular structure. Okay, Cassandra provided you a tabular structure, which means whatever objects you have, whatever ORM you have, you can use it with Cassandra. Okay, for ORM you have Hector in on top of Cassandra, which makes it possible for you to convert the data into relational format from object format. In case of MongoDB, you don't require ORM. You basically store the data directly from object into the database, because MongoDB is sort of an object storage. All right. So in HBase, you have billions of rows and millions of columns, and Hadoop is probably the best way to run MapReduce jobs on huge data set. Best if you can use Hadoop and SDFS stack already. And okay, so search engines analyzing you can use HBase for storing lot of data you of search engine, analyzing log data, any place where scanning a huge two-dimensional data is required. Okay, Join less means you are not joining multiple tables. So okay, so another decision point is, if you already have Hadoop stack, which means running HBase will not take an additional amount of effort from your side. You already have the stack in place. You will be using the same HDFS. Therefore, if you already have Hadoop stack, the chances are that the HBase will suffice for you. If it is not, if you don't want to set up Hadoop stack and you want a proper storage for the huge database, huge data, then you might prefer using Cassandra. Okay. And also note that in case of HBase, the consistency is strong, which means the availability it suffers from availability. While in case of Cassandra, the it's a tunable consistency. We can say strongly consistent, or we can say eventually consistent in case of Cassandra. So those are the reasons you might want to take different approaches. All right. So that's pretty much for today's discussion. Now I would like to take you through a project which is mandatory for all. Okay. In this project is basically, I would like to take you through. All right. So we have this is yours, right? Yeah. Is everybody with me? So session number 12. So the project assignment is this. Okay. You click on this, not this. This is, what is it? What's happening with this? Why doesn't it? Oh, great. Now it's working. So we can open this. All right. So the project is, are you guys with me? So yeah. All right. All right. Great. Great. So here we are. So we need to do a sentiment analysis of a keyword called Iron Man in this example. Okay, I'll take you through this approach, and I would want you also to go through this approach. So the problem statement is, the objective of the exercise is to do the sentiment analysis based on tweets data from the Twitter. Okay, so all we need to do is read each tweet that contains Iron Man on related keyword, and if that tweet is negative or positive, and how much positive or how much negative it is, we need to basically find out. Okay, against each tweet, against each country, we need to plot the graph. Okay, now let's go into the details. So here we are outlining the primitive strategy, very simple strategy for sentiment analysis for the movie called Iron Man using Hive. It is up to you whether you choose exactly same step, or you use different strategy altogether. There are various deviations possible. There are various deviations possible. Okay, you can change the approach of. r- Okay, right now there are multiple. Let's understand it first, and then we'll go through the deviations again. Okay, now, and there are those who are really interested in the research. You can go through these. This is machine learning kind of approach. If you more on data sciences part. So first of all, log in to Hue at this port and open this particular file. Okay, I think it'll ask me to click on that link again. Yeah, it is opening. All right. So the day here you can see that in this folder there are two folders. One is data, other is Hive. Hive contains queries, data contains actual data. So I've already downloaded the data using Flume from Twitter. Okay. Here Twitter raw contains the zipped file of the actual data, which Hadoop can handle or Hive can handle easily the zipped folder. Like, now you can see that this is a gz file, and this is inside it is essentially a JSON structure. Okay, that's what is the data. Let's look at what else is there in the data. So there are many files under this folder, all are zipped, and all are zipped JSON file. Now there is something called time zone map. Time zone map is nothing but a tab separated file, and it lists down the relationship between time zone and the country. Okay, time zone as the country. You will understand why, because inside inside our Twitter data we did not have the country, but we got the time zone. Okay, we got the time zone. Based on time zone we will infer that from which country the tweet was posted. Yeah, is the voice breaking for everyone? Okay, so I was describing that the first is tweets raw. It contains the full data about all the tweets on a particular date, on a particular period. So you can have a look at this. To make it little cleaner, I will take this data and use JSON formatter website. So here you can see that this data is it visible to you? Okay, you can see this data. It basically has all the details. This is the text of tweet, and then you have the URLs. Okay, posted in the tweet. Okay, you can see that URL in the tweet, and also you have you see this URL which is extended. Now you also have the created date which contains the time zone, which not this one, and this is the user details. Okay, the location is German, and yeah, and description is something. This is the profile image. Okay, this is the screen name as in the Twitter kind of thing, Twitter handle. Okay, so based on this, and these are the profile image, so we have all the details about the user, and the and here time zone would be there. Yeah, you can see time zone is null in this case. So we have such kind of a collected lot of objects which can be used. All right, now this is one part. So this is the full tweets data. So locate the data. Once you have located, let me open it once more. Okay, so tweets contains tweets data. There is time zone relation between the time zone and the country, and then there is a dictionary. Now dictionary is something very important here. It's a tab separated dictionary. Here it gives the meaning of each word. This dictionary, it basically, given a word, it tells you whether it's adjective or is noun, or whether it's a negative or positive. It tells you all these details. Okay, so all we need to do as a result of this exercise, join the dictionary and join the dictionary and tweets, prepare the results, and then also figure out the country of each individual tweet, and then plot the graphs. It's as simple as that. Okay, and we will do this using Hive, because this data would be really huge in case of if we are dealing in production environment. Okay, so we have logged in, we have located the data. All right, now follow this particular query. This is important. So go through upload, and then you click on Hive, and there you will ignore all other queries. Okay, ignore all other queries. Let's just focus on this particular query and this file. You will need to download this file into your local machine, into Hadoop 1, Hadoop 2, Hadoop 3, or anywhere else, because you need to run this. While running ddql, you will have to say add jar. Okay, why? Because we are going to load JSON data as Hive tables. And to load the JSON data, you need a library. I have put the library there for convenience. I have put that library into HDFS so that you can download it and run it. Okay, so you will launch Hive command. You will add jar. When you add jar, this particular jar, this file which we have you just copied to local file, will get loaded. Also, before doing any of this, create your own separate database. Okay, create your own separate database so that you do not create these tables or override these tables into anybody else's data store. Okay, next is create an external table like this. Okay, okay, and here you can see that we are saying raw format as JSON survey, and we are also specifying the location of the data. Okay, this is the location of the data. All right, now that is the location of the data, and this is our row format. Yeah, you can use the same path as long as you are using external table. Okay, because in case you did not use the external table, right, in case you drop the database, my file will get deleted. Okay, that is, and similarly you can also use the same path in case of dictionary also. All right, and so we create these three tables which are external tables. We create them external tables so that you do not alter them. Next is that we create a view. Okay, we create a view. We clean up the data such that we have ID of the tweet, and then we have timestamp of the tweet, and what was the text which was said, and the user. So out of the full data set, we are only picking these four columns. That's all. Okay, because other columns we are not going to use anyway. Now after tweet simple, we are going to clean up the data by by bringing the country, by joining the data with another table and bringing the country from that table called time zone map. Now we'll have ID, timestamp, text, and country. Okay, instead of time zone we have country. Next, once we have these four columns, now will be the time when we break down the sentences into words using explode and sentences. And once that is done, first sentences will break the full tweet into words, and then explode will break that into one word per row. And after that is done, you join this table After you are done with exploding and only picking up those few values, you will join this table with the dictionary. You can see that with the dictionary. Now in the dictionary, again, let's go through the dictionary. Dictionary contains what kind of word is it, the length of the word, then the actual word, then whether positive or negative, then stamped whether it's ing or ed, and then polarity. Okay, we'll use polarity. Okay, so what we have done is we have broke down tweets into word per line. Now we are joining this word against a dictionary. We are joining this word against a dictionary, all right? And then, okay, so once we do that, we will be able to say if it is negative, the keyword there in the dictionary is negative, then mark it -1. Keyword is positive, mark is 1. And once that is done, we sum up the polarities. We sum up the polarities and say that if the sum is 0, then greater than 0, then tweet is positive, then negative, and so on. We are grouping by ID, so that grouping by ID means we will sum up the negative or positive polarities of all the words. We will sum up the polarity of each word in a tweet and do the group by. Once that is done, we will put everything into the database table, okay, and we'll try to draw it, okay. We'll try to plot the graph using this. So once this is done, your half work is done, only presentation is left. Now, to do the presentation, you can use anything, okay? You can use anything which can connect to the JDBC driver. All right, you can basically in Hive in your Hadoop folder there'll be a Hive driver. You can download that driver and start using with any of the presentation layer you want to use. Okay, and anywhere in the presentation layer you should say that server is this and type is Hive server, or okay, and provide the login password. Port you should provide as 10,000. Okay, but here in this case what we are saying is you can install Hortonworks Excel driver, and from your Microsoft Excel you can directly contact our Hive server and plot this data into your Excel sheet. Okay, so once this text is successful, once you have installed the driver, you can launch the text Hortonwork ODBC driver DSNS setup. And once that is successful, that means you are in a position. You go through, then you start executing the queries, okay, by selecting this particular data source and selecting the various columns. So basically, you will be calling all your functions on tweets bi. Okay, so you will be querying tweets bi because this is what is prepared after churning all of the data above. Sounds good? All right, so once you are able to do that, you can present the data here in this form. Now, other than this, what I was emphasizing upon was you can go for a little deviation. Okay, if you noticed, what we have done is we have simply summed up the polarity of all the words in a sentence. Instead, you can first uh, change the definition of polarity such that you give 1 to a negative word, and you give 2 to the positive word, and 0 to the neutral. And in case the sum is odd, the tweet is negative. Okay, because right now what we are doing is we are assuming that in case somebody is writing a negative sentence, they will write all the negative words. The more the negative words is there, the more is your the more is the negative polarity of a tweet. But that's not true. So you can change the approach such that you put odd number for negative word and even number for positive words, and then sum it up. And in case the resultant is odd number, that means it's a negative tweet. If the resultant is positive number, then it's a positive tweet. Why? Because if there are two negative words, which means two odd numbers, they will make the positive words, which means they will make the even number, right? And that's what I'm saying. So change the approach of summing up negative and just summing up the polarity. Okay. Although this approach also is some way okay, because the only problem with this approach is that in case there are two negative words, the result will be -2 rather than 0. Okay. Yeah, that's what I'm saying, Anand. So we should take that into consideration. So it is using the dictionary. We are just comparing. We are picking up the meaning of a word, positive or negative, by joining our data with the dictionary. Or yes, it is freely available to everyone. You can get a reasonable sample data from the Twitter. And a very simple one I have already put in under the Senti here, under data. Okay, okay. I need to see. Yeah, under sentiment files. Yeah. So there is a Flume folder under sentiment file. You can look at the Twitter config. It's basically a Flume config. If you remember, we had sources, sinks, and it's basically giving these secrets. So all you have to do is create your account with Twitter, mention your consumer secret and consumer key, and then you can uh, start the Twitter. Okay, you can start the Flume example the way we had run in past. Okay, so Twitter gives us a sample of data. It doesn't give us the full data. Okay, and sample is good enough. It's actually big enough for most of the computing. All right, so yeah, coming back to the project. So the other one is you can either change this approach, or you can use a completely different algorithm to compute sentiment based on NLP. This particular document actually covers in details various approaches available in sentiment analysis. Okay. Also, the easiest route. So dictionary also I downloaded from somewhere. Okay. These are the standard dictionaries available to us. Okay. Next change you could do is you start afresh with a different movie. Once you have set up your own Flume pipeline to download data, you can start afresh for a different movie. Create your own program to download data from Twitter, or you could basically use Pig instead of Hive. You can rewrite whatever we did in SQL using Pig. Okay, this will these two will be the way easiest change. This is going to be the easiest change, and this is little difficult. Okay, here you can start afresh only if you set up your own pipeline. Okay, or you, instead of using BERT, you may use sorry, instead of using the Hortonworks driver for Excel, you could use the other display of the data, such that data driven graphs, data driven JS, D3JS, or you could use TableView, or you could use BERT. All right. So those are the deviation on the presentation layer. These are the deviation on getting the data. This is the deviation in the approach, these first three. Okay. So you can try, you can try whatever deviation possible, but first try to run the Hive query. If you are confident about running Hive query, you've already done, then you should plan to do something little more advanced. All right. So that's about our project. So first, so as a, and at the end of it, you should have your own database tables. And just send me a link to your database table. I'll review them. Also, send me the Excel sheet. If you create those Excel sheet, send me the Excel sheet as the project summation. Okay, and I'll have a look at it. So lab will be available till the last, till June 20 for you. 20 more days. 15 more days actually. 13 more days. Okay, here. Okay, which means May plus June, and this is uh, how many days? 30 plus 20 is 30 plus 20 is 50 days. Yeah. All right. All right. Any questions for me now? No questions. All right. So that's pretty much for today. So once you are done, first you have to tell me where is your data. Give me the database name. Second, you have to send me the Excel sheet, whatever you create. In case you are not using Excel sheet, you are using some other DB tool, send me the screenshot of that DB tool. All right. So, okay, then this completes our sessions. We started with 11 sessions. Now we have 12 sessions. So in case you hit an issue, drop us an email. In case the issue is something which we are not able to figure out over email, then we can have one-on-one, no issues. All right. All right. So in today's world, the goodbye is not really a goodbye. We'll stay connected. And maybe some of you have already sent me a LinkedIn request. You can send me a LinkedIn request, and we can stay connected over there. And also uh, stay connected in the sense that then go through our forum. If you have any question, or if you see some question unanswered, answer that question. That will keep you updated with the technology. And also, if you we will be we'll keep on sending you the job descriptions as and when they come to us. We'll keep on sending those job descriptions to all of the people. And okay. All right. So Stay connected, and if you have any questions, reach out to me, and feel free to feel free to ask, or feel free to get connected. All right. Thank you, Lakshmikant. I really appreciate the class, and I've got really brilliant questions. And thank you, Basraj. Thank you, Pravita. Thank you very much. Thank you, Anand. I look forward to interact with you. And all right. Okay. So that's pretty much for today. All right. So feel free to refer your friends. Okay. Your friends will get a referral discount for our future classes. All right. Great. Great. Do you have anything else to say? You want to unmute yourself or say something? Nothing? All right then. So I should hang up now, and then uh, feel free to get connected. And yeah, and I mean, the session is not the end of it. If you have in future, if you have any questions or any problem, feel free to drop an email, and then I can, okay, then I can help you maybe in if you are stuck somewhere. All right. Thank you all. Have a great time ahead. Bye bye. All right. All right. Let me save the chat logs. All right. Thank you very much again. Bye bye.